Welcome to the deep dive. Today we're tackling something pretty universal, I think, for anyone dealing with digital stuff. It's that constant worry. Is my data safe? Is it fast enough? Will it actually be there when I need it? You know that feeling, right? Losing files or just waiting and waiting for things to load. It's frustrating. But there's a foundational tech that aims to fix this. We're talking about RAID, that's R-A-I-D, the redundant array of independent disks.
Yeah, RAID is really a cornerstone. It's designed to hit both those points. Data safety through redundancy and often better performance too.
Exactly. So our mission today is to cut through the noise and give you a clear map of how RAID works, specifically in the GNU Linux world. We want to demystify it a bit, look at the main options without you needing, a PhD in storage.
Hopefully you'll walk away with some real aha moments, understanding how you can protect your data better, make it faster on Linux systems.
And we'll focus on the two big paths, hardware RAID and software RAID. Okay, so let's unpack this first one. Hardware RAID, you kind of hinted it's like a separate box. What does that actually involve?
Right. So hardware RAID fundamentally relies on a dedicated controller card. You'll see names like Broadcom, maybe LSI, or Microchip, Adaptec. It's actual hardware, a card you plug in with its own processor, its own memory, all just for managing the disks.
Ah, okay, so it's not the main computer's brain doing the work. It's got its own dedicated little brain just for the drives.
Precisely. And the key thing is you set it up outside the operating system. Usually there's a utility baked into the system's BIOS or, the newer UEFI firmware. You configure the array there.
Before Linux even boots up.
Exactly. And once that's done, the operating system itself, it doesn't see the individual physical disks at all.
So Linux just sees what? Like one big hard drive?
Pretty much. It just appears as a single block device.
Right.
Might show up as devsda, for instance. The OS has no idea there's a complex RAID array underneath.
That's a really different way of thinking about it compared to, say, plugging in a USB drive. So what's the upside of that abstraction? For a sysmin, maybe?
Yeah. Well, the big upside is performance and offloading. Because the dedicated card handles all the RAID calculations, parity checks, rebuilds, whatever, your server's main CPU is completely freed up. It can just focus on running applications. That can be a massive performance win.
Right. And I guess that separation, that hardware isolation, might be important in some big enterprise setups.
Absolutely. Often mandated, even. Plus, management is done through tools specific to that card vendor. You'd use something like StoreClay or MegaClay, not standard Linux tools.
Okay, vendor-specific tools. So you're kind of locked into that ecosystem once you choose the card.
To a large extent, yes. For monitoring health, managing the array, you use their software.
I can definitely see the appeal for, heavy-duty servers where performance is everything.
Okay.
But that dedicated card sounds like it could add cost, right?
Yeah.
There may be complexity for, I don't know, a home lab setup.
It absolutely can. Those high-performance cards aren't cheap. And yeah, learning the vendor tools can be another hurdle. It's a trade-off. Maximum performance and isolation versus cost, and maybe a steeper learning curve, which often pushes people towards the other main path.
Okay, that makes sense. So that's hardware RAID, powerful, isolated, but maybe pricier and more complex. Let's pivot then. Let's talk about bringing that control into GNU Linux itself. Software RAID. This sounds like where things get, a lot more flexible, maybe.
Definitely more flexible. With software RAID, you're using the operating system's own resources, the main CPU, system memory, to manage the array. And because it's software, it opens up a whole range of different ways to actually implement it.
Right, so it's not just one thing called software RAID. There are different flavors within Linux.
Exactly. There are really three main ways people do software RAID on GNU Linux these days. First, there's the real classic approach. The kernel's mdadm subsystem, been around forever, super solid. Then you've got more modern takes, where the RAID smarts are built right into the file system itself, think BTRFs or ZFS. And the third way is using the logical volume manager, LVM, which also has RAID capabilities built in.
Okay, three distinct approaches.
Yeah.
Let's start with that classic one. mdadm, I feel like I've seen dev devices mentioned forever. What's the core idea there?
Yeah, mdadm is definitely the bedrock for a lot of Linux RAID. It's mature, very stable, and runs directly in the kernel, so it's efficient. How it works is it creates these virtual RAID devices. They appear in your dev directory as devmd0, devmd1, and so on. These MD devices are what you format with a file system and mount, just like a regular drive.
So it's like a software layer creating these virtual disks out of physical ones.
Yeah.
And I assume the mdadm command is how you actually build and manage these.
That's exactly it. The mdadm utility is your command line interface for creating arrays, adding or removing disks, checking status, handling failures, everything. It's powerful.
Okay. And this is where we get into all those different RAID levels, right?
Hmm.
0, 1, 5, 10. It can seem a bit overwhelming. Can you walk us through the main ones MDAM supports and like why you'd pick one over another?
Sure. Each level really is a different balance of speed, capacity, and safety. Let's break them down. First, linear. Super simple. It just sticks disks together end to end to make one bigger volume. No speed boost, no safety net, just combined space, maybe for temporary stuff.
Okay, just more space. Got it.
Then RAID 0 or Stripe. This is purely about speed. It splits data across multiple disks, writing and reading from all of them at once, so potentially much faster. But, and this is the huge catch, if any single disk fails, all your data on that RAID 0 array is gone. Kaput.
Whoa. Okay, so high risk, high reward on the speed front. Maybe for scratch space, like video editing.
Exactly. Non-critical data where speed is paramount. Definitely not for your family photos.
Right. Okay. What's next?
RAID 1, the mirror. This is all about safety. It writes identical copies of your data onto 2 or more disks. If one disk dies, the other one just keeps running with an exact copy. You lose capacity. 2 1 TB drives only give you 1 TB of usable space, but your data is safe.
That sounds perfect for, like, the operating system drive or really critical data where losing it is not an option.
Precisely. Then you get into parity RAID. RAID 4 and RAID 5. These try to balance speed, capacity, and safety. They stripe data like RAID 0, but they also calculate and store parity information. This parity lets the array rebuild the data if one disk fails. RAID 4 uses one dedicated disk just for parity, while RAID 5 spreads the parity across all the drives. RAID 5 is probably more common. You lose the capacity of one disk for parity, but you can survive a single drive failure.
Okay, so good middle ground for servers, maybe.
Yeah.
Capacity and some protection.
Yeah, very popular. But what if losing one disk isn't enough protection? That's where RAID 6 comes in. RAID 6 uses dual parity. It calculates 2 different sets of parity information. This means it can survive 2 simultaneous drive failures.
2 drives. Okay, that's significantly more resilient for really critical stuff, I imagine.
Definitely. Especially important during a rebuild when the remaining drives are getting hammered. Losing a second drive during a RAID 5 rebuild is catastrophic. RAID 6 protects against that.
Makes sense. And the last big one is RAID 10.
Right, RAID 10, sometimes called RAID 1 plus 0. It's basically a stripe of mirrors. You take pairs of disks, mirror them, RAID 1, and then you stripe your data across those mirrored pairs, RAID 0. You get the redundancy of mirroring and the performance boost of striping. It requires at least 4 disks, and you get half the total raw capacity.
So best of both worlds, almost. Speed and safety, but maybe less capacity efficiency than RAID 5 or 6.
Exactly. Often used for things like busy databases where you need both high I/O performance and very high fault tolerance.
Wow. Okay, that clarifies the levels a lot. It really hammers home that there's no single best RAID level. It depends entirely on what you need: speed, safety, capacity, or some mix.
That's the key takeaway. Understanding those trade-offs is crucial for making the right choice for your data.
Okay, so mdadm is the classic kernel-level way. But you mentioned newer approaches where RAID is part of the file system itself, BTRFs and CFS. How does that change things?
It changes the perspective quite a bit. Instead of RAID being a separate layer under the file system, it becomes an integral part of it. These file systems, they manage the storage volumes and the data layout, including the RAID logic, all in one unified system.
Interesting. So less layering, potentially more integration. Let's look at BTRFs first. What's its approach?
BTRFs, the B-tree file system, yeah, it has integrated volume management. You give it a bunch of devices, and it treats them as a single storage pool. Then within that pool, you can tell it how to arrange the data. It supports RAID 0, RAID 1, and RAID 10 natively.
Okay, 0, 1, and 10. What about 5 and 6? I hear about those sometimes with BTRFs.
They are implemented, but the general consensus and the official status is that BTF's RAID 5 and RAID 6 are still considered unstable. There have been data loss bugs in the past, the so-called RAID hole issue. So while technically there, most people would strongly advise against using BTF's RAID 56 for anything important right now. Stick to 0, 1, or 10 if you use BTRF's RAID.
Good to know. Definitely unstable is not what you want for RAID.
Okay.
Then there's the other big one, ZFS. Often called OpenZFS now. This one gets talked about a lot, especially regarding data integrity.
Oh, yeah. ZFS has a massive reputation, and largely deservedly so, for being incredibly resilient. Like BTFS, it's an integrated volume manager and file system. It has its own concepts. You create pools of storage using the zpool command. These pools are built from VDEVs, or virtual devices. A VDEV could be a single disk, a mirror, or one of ZFS's special RAID Z levels.
Okay, pools and VDEVs, so it has its own terminology. And RAID Z, how does that compare to standard RAID levels?
ZFS offers mirror, which is like RAID 1, but then it has RAID Z. There's RAID Z1, which is similar to RAID 5, survives one disk failure. RAID Z2, like RAID 6, survives 2 failures. And even RAID Z3, which can survive 3 drive failures. It also has DRAID, which is a bit more complex for distributed setups.
3 drive failures. But what's the real killer feature people talk about with ZFS? Not just the redundancy levels, is it?
No, the absolute killer feature is its relentless focus on data integrity. ZFS uses end-to-end checksumming for everything. Data, metadata, it checksums it when it's written. Then, when you read that data back, it verifies the checksum. If it doesn't match, meaning the data got corrupted on the disks somehow, what they call bit rot, ZFS can detect it. And because of its copy-on-write nature and the redundancy in RAID Z or mirrors, it can often automatically repair the corruption using good data from another disk or parity information. It self-heals.
It actually fixes silent corruption. That's amazing. Traditional RAID wouldn't even know the data was bad, right?
Yeah.
Just rebuild garbage if a drive failed.
Exactly. That's the danger. ZFS actively prevents that. It guarantees that the data you read is the data you wrote. That's why it's so heavily favored in professional environments, archives, places where data integrity is paramount.
That self-healing is a game changer. But I have to ask, does all that power come with maybe a steeper learning curve than MDAD? Or more specific hardware needs?
Yes, that's fair. ZFS does have more unique concepts, its own commands, zpool, ZFS. The learning curve is generally considered steeper than MDAD. And while not strictly required for, say, home use, ZFS strongly benefits from and was designed around using ECC RAM error-correcting code memory. This helps prevent memory errors from corrupting data before it even gets written to disk, maintaining that end-to-end integrity.
Okay, so more demanding, potentially, on the user and the hardware. But the payoff is that incredible data protection.
That's the trade-off, yeah.
Right, one more software approach to cover it. Logical Volume Manager, LVM. Lots of Linux users know LVM for flexibly managing partitions, but it does RAID too.
It does indeed. LVM2, the current version, integrates RAID functionality right into its framework. It offers another way to get software RAID, often combined with LVM's other management features.
How does that work? Is it layered somehow?
Yes, LVM is inherently layered. You start with your physical disks or partitions, which you designate as physical volumes or PVs. Then you combine one or more PVs into a volume group or VG. Think of the VG as a big pool of raw storage space. And then from that VG pool, you carve out logical volumes or LVs. And these LVs can be configured as various RAID types.
Ah, okay. So the RAID is happening at that logical volume level within the bigger volume group pool. That sounds really flexible.
It is. That's the main appeal of LVM in general, and its RAID is no exception.
What RAID levels does LVM support? Is it the standard set?
Yep, it's most of the common ones. RAID 0, 1, 4, 5, 6, and 10. You can create an LV with any of those profiles.
And the big advantage here, compared to maybe MDAB, is that LVM flexibility, like resizing things.
Exactly. LVM excels at things like dynamically resizing volumes. You can potentially grow or shrink LVM RAID arrays, migrate data between PVs within the VG, all while the system is running. That level of abstraction and flexibility for managing storage on the fly is why many sysadmins like using LVM, including for its RAID capabilities. It gives you agility.
Okay, fantastic. So we've really journeyed through the landscape here. Started with hardware RAID, those dedicated cards, all about performance and isolation.
Separate, self-contained.
Then dove into the software world within Linux. We had VMDAM, the solid, reliable kernel classic with all its levels.
To workhorse for many years.
Then the integrated file system approaches BTCRFs with its potential, and ZFS with its incredible focus on data integrity and self-healing.
Representing a really powerful evolution, especially ZFS.
And finally, LVM, bringing RAID into its super flexible volume management framework.
Adding that extra layer of agility.
And the point of all this, for you listening, isn't just tech trivia.
No, absolutely not. If you're setting up a home server for your media, managing critical business data, or even just curious how your computer keeps things safe, these are the mechanisms.
Understanding these different ways to do RAID really gives you the power to choose wisely. You can balance the cost, the speed you need, and how much protection your data really requires.
It lets you make informed decisions for your specific situation.
You get to control your data's destiny, in a way.
It really does give you that control.
So as you think about your own digital setup, maybe the question isn't just, am I backed up? It's also, how much active control, how much architectural choice do you want over the system safeguarding your most valuable information? And which of these fascinating paths are you going to explore next?